Hello. Switzerland did what? Oh no. Alright. Okay. Good morning, Eugene. We need to talk about Switzerland.
Huh? They never take a side on anything.
That's all changed. It turns out that during all these years of staying neutral, they've been constructing a weapon to destroy the world. They just made their final breakthrough thanks to an aspiring undergraduate particle physicist. I need you to assemble a team.
An A team?
An A team.
Where'd you draw that?
Alright, I'm looking for a really smart person who's good at math. And if you can solve this equation, is there anyone?
I can solve it.
The janitor?
The janitor.
You can barely use that broom right. That dumb janitor. This is impossible.
Is that right? Oh my god.
It is.
That means you can also solve it.
Morning, gentlemen. We have a top secret mission ahead of us, and I need to recruit one of you to do it.
I'm ready.
Wait,
I like
what
the
is it?
initiative. You have to beat me in a game of tic-tac-toe.
Oh, I can do it. I can do it.
No, you can't.
He's got a lot
Can't
of-
do it.
He can't do it.
No.
But that's
So
a game
what
for
do you think?
geniuses.
I'd send him.
It's like a reverse Captain America right here.
I think that's.
You ready for the job? Okay, let's do it. It's like a race against time. It's in the bag.
Oh! Yes!
Gentlemen, Sweden's cruel plot to end the world is right now imminent. So far, we've tried these drastic methods to solve this problem. Addition, multiplication, a squared plus b squared equals c squared, Gödel's incompleteness theorem. But we are only left with questions. I heard you guys are the best in the West, and so I need you guys to give us some insight.
We'll see what we can do.
I hope so.
Okay, guys. I think I've done it. So, I just started thinking to myself in my long time of pondering about this issue. How does one stop a missile from really far away? Well, obviously, the only way to do that is if you know the potential away from 4-point charges, which is clearly the setup that Switzerland is using to, ignite their, missiles and stuff and just launch them and stuff. So, you have clearly you have 3 times some characteristic point charge up here. You've got 1 characteristic charge below it, and you got 2 negative 2 Q's on the sides, equally distant from the origin. So, I mean, I don't know if I have to explain this to you guys, but clearly this is a multipole expansion problem. I mean, it's screaming at you. It's just begging to be multipole expanded. And so the first few terms of this expansion, obviously, we know that that the first term of the expansion is a monopole term, and the second term is a dipole term, and we just keep going. We have more poles, we got a ton of poles in here.
Right.
Poles.
Right.
And then
At least 2.
at least 2 poles. So So now all we really have to do is just find the first non-zero term in the sum, and we'll know the potential far away to first approximation, because we only need a first approximation, because it's not like a big deal. We don't need to know it exactly. So we got the first term, we're good. So that's what I started to do. The first term, we got the monopole term here. We got 1 over 4 pi epsilon naught r, and you got to integrate over all space of your charge density. But of course, people at 2 Mercado know that these can be represented as point charges, just as you've seen in delta functions can describe them. So as long as you incorporate that space, that the integral over all space is equal to 1 for each one of these integrals. So that simplifies all this to just 3q plus q minus 2q minus another 2q. And Eugene, can you tell me what that equals?
I think it's 0.
That's right.
My God.
There is no monopole term. So now all we have to do is just find the dipole term, and hopefully that's non-zero, and we'll save the world.
I'll go get help.
No.
Just hang on.
No, there's no time. Switzerland's coming. Oh, here, take this pen. You have to solve the problem for me.
I'll make you proud.
Swedish music. Swedish music.
Before his tragic passing, JT told us that this is the dipole term. So we're going to rewrite that like this, where P is the dipole moment, which is defined to be this integral. We could do all these integrals for the charge density, which JT already showed, but since the fate of the world is on the line, we're going to jump to this formula for the dipole moment, which works for point charges, where the dipole moment is just equal to the sum of the charges multiplied by their position vectors. So the result of that is this relation. If we plug in all the position vectors, we will group according to the z components and y components. The y components cancel out, and we're left with 2qa in the z hat direction for a dipole moment. If we rewrite this dot product as just the magnitude of p times the cosine of the angle between the dipole moment, which is in the plus z direction, and wherever we're at, which is denoted by r, then we'll get this, and we'll plug in the magnitude of our dipole moment, and we'll get a non-zero term in our expansion. So, I think we've done it.
No.
It's been a long day without you, my friend, and I'll tell you all about it when I see you again.
This devastating moment reminds us that sometimes scientists have to risk their lives to fight for what we believe in. And unfortunately, this day is to remember the very best of us, who risked his life to prevent Switzerland from destroying the world.
You can snap. Yep. You snap slow. There you go. Yeah. Okay, mine's in 10. Good mine in 10. Good morning in 10. We're going to talk about Switzerland.
Huh?
Yeah, that's a tie.
That's a tie.